started the recording, so we should be all set.
Okay, so thanks for joining, everyone. We're going to be going into our next recitation. We're going to start off with convolution. That's going to be the topic for today's recitation. So convolution. So I always like to start off with why it's important or why are we learning this. Convolution, I know you've already heard me say this before, but this is a pretty critical topic. I'd say arguably one of the most important in all of signal processing. It's pretty foundational and pretty fundamental. And basically what convolution is in very broad and big picture terms is you're just trying to find the similarity between two different signals. So what that looks like graphically is if you have, signal x1, and you have signal x2, process for this is you can first label one as the actual signal, and then you can call this one the kernel. And you basically flip this one, so you time reverse it, right? So you flip it like this, and then what you do is you run it across the kernel across the entire signal, kind of like a moving average, but you point by point run it across like that. And for continuous functions, you're going to want to find places where it overlaps, and we'll go into some example problems later, but you'll basically start from over here, and then you're able to calculate a new function that's somehow mapping its similarity. So the result of convolution. So once again, you're taking this kernel, you're time reversing it, and then you run it across the initial signal. You go and try to find how it's similar by finding areas of overlap. Okay, so now we're going to hop into the actual problems. So before we hop in, how can we solve convolution problems? So it's pretty methodical. And we're going to start with continuous functions. That's going to be all of today, is just continuous functions. Okay, so the first step is going to be, well, I guess before even we hop in, so we're going to want to go off the overall formula. Which we want to say where y of t is equal to x of t convoluted with h of t. So here, this could be seen as your result. This could be seen as your signal and your kernel. Okay, so the actual formula for this, and just as a reminder, this symbol here, it's not multiplication, it's convolution. And what this formula actually looks like for continuous functions is the integral from negative infinity to infinity of x of tau. This is a tau, not a t, multiplied with h of t minus tau, d tau. So here, this is a t, and this is a tau. And the tau is this dummy variable. Okay, so now going into the actual steps. You have the formula. How can we actually solve convolution problems? So we have two signals, we want to convolute them. How can we solve that? The first step, and we're going to follow this for all the problems today in recitation. It's pretty methodical. So we're going to replace t with this dummy variable known as tau. That's what I alluded to above. That's the t, and here's the tau, right? So we're going to replace t with tau. So h of t comes, or sorry, yeah, h of t becomes h of tau. And x of t becomes x of tau. Okay, so now we're going to time reflect. Remember how up here I said we're going to take the kernel and we're going to time reverse it? So now we can employ that. we are now going to time reverse the kernel. So this now becomes h of negative tau. Remember our signal transformations. And then we're going to shift h of tau to the left, all the way to the left. So remember how I started off all the way over here? So that's the first step. So even before there's no overlap. Right, so we shift it all the way to the left, and then we slowly move it to the right, finding areas of overlap, and then taking the integral. So we're going to shift the kernel to the left. So h of t minus tau. And then we can take the integral, because it's a continuous signal, right?
Yeah.
Okay. So these are the overall steps. This is why we're doing convolution. Everybody follow me so far? So yeah, Isabella, the asterisk is, like Emily says, asterisk is always convolution. Okay, everybody feeling good? Can we get some thumbs up or some unmuting of the microphones, guys? We feeling good? Isabella, 80, you feeling okay? Megan? Okay. So let's continue, guys. So the problem we're going to start with today. Yeah. Okay, so problem 1. So here we're given 2 signals, okay? The x of t equals, it's going to be a piecewise function where it's equal to 2 from 0 less than t less than 2, and then 0 otherwise. Okay? And then we're also given that h of t is equal to 3, 0 less than t less than 1, and 0 otherwise. Okay, so this is given. This is what you would get on the actual problem. Given. So the first step, always, for 99% of scenarios when you're given 2 functions, just so you understand the situation, you understand what's going on, is you should graph them, okay? So the first step is going to be to actually graph them. So let's start with graphing x of t. Okay, can anybody help me graph this? So before we do any of the convolution stuff, we haven't replaced anything with dummy variables or time reflected anything. We're just graphing this x of t. Do we remember how to graph piecewise functions? Okay, I'll start us off. So we're going to have 1, 2, 3. 1, 2, 3. That's all the help you guys are getting. Who can help me graph this? Let's have somebody unmute. That'd be nice.
I thought it'd be cool to have the annotation thing that Alpha did last time on the whiteboard. I was gonna draw the graph,
Yeah,
but
you can annotate it. You can annotate.
yeah. Wait, can I?
I think they're disabled.
No, it's okay though. I could just describe it. So you would basically just have a horizontal line at 2 for x of t between 0 and 2, and then you just have flat lines for everything else with a little connecting part in there.
They're not straight line, guys. Let me fix this real quick. But you are right on the money. Great job, Jade. And also, I think it was Megan who unmuted, right? I think so. Whoever unmuted besides Jade. Thank you both. Okay. So we're gonna have this function. It's going to be 0 besides between 0 and 2 on t, and then in that time interval it'll be equal to 2. Okay, so now we're going to also graph h of t. Okay, and once again, it's going to be pretty similar. It's going to equal 3 from 0 to 1. Okay, so here's our two functions. Okay, so here's our signal. And here's our kernel. Okay, so does anybody remember the first step? I'll give you a hint. We're going to replace this t with our dummy variable tau. It's not really a hint, I just gave you the answer. You're welcome. So we're now going to turn x of t to x of tau and h of t to h of tau. Okay. And so what does this look like? It is the exact same thing, but we just replace it with tau, right? So all we did was we changed the variable. It's like saying, it's like calling, instead of calling it t, we call it x, y, z, right? So we didn't really change anything about the properties of the signal. We just changed the variable that we're defining, right? So now this is no longer t, this is tau. And this is no longer t, this is tau, right? Same for h of t. So same exact thing, right? We're not changing any properties of the actual signal. We're just replacing the variable. So this would be step 1, replace with dummy variable. Dummy variable tau. Okay. Everybody feeling good? It's a pretty chill step. So I'll keep going, but please interrupt me if you have any questions. Okay. So now we're all done with x of t for now. We're going to focus on h of t. And so the second step, if you guys remember, we're going to be shifting it to the left. Or sorry, we're going to actually flip the kernel first. So now we're going to do time reversal. So now we're going to have h of negative tau. And so this is going to look like something like this. The actual shape of the graph is going to remain the same, but it's going to get flipped. Okay, so something like this. Okay. Everybody follow me so far? We just flipped it over the y-axis. Okay, and now step 3 is we're going to shift it. Okay. So
we flipped h of negative t, right?
we flipped h of tau, right? So just starting from the top. So here's what we were given, right? Just starting from the top, just a quick recap. So here's our h of t that we're given, right?
No, yeah, but so wouldn't that mean that it wouldn't be on 2, it'd be on 3, the top
Oh yeah,
part.
great catch.
Yeah.
See, 80, you're now promoted to our new A+ student. I'm sorry, Jade.
Thank you.
Okay, it should be like this. Thank you, 80. Okay. I'm just making sure you guys are paying attention. Looks like you guys are. So now we're going to shift it. We're going to shift by t. Okay. So now what we're going to do is move it to the left. So there's absolutely no overlap between h of t and h of negative tau and x of tau, right? So that's going to look something like this. You might have keeping track of everything. Here's our dummy variable tau. And here's t. Okay. So we're going to look something like this. Everybody follow how I got here? So here's our h of negative tau. And by subtracting by some arbitrary t, we don't know what the value of this is. We can call this t minus 1 and t. Right? So we're doing a time shift by t. Okay. So I'm going to move on to the actual convolution now. So please feel free to hop in if you're struggling. So the last step is to analyze the integral for overlapping time intervals. Okay, if you have any questions, please feel free to interrupt. Okay, so what this might look like, guys. So here's some possible scenarios. So we could get a situation where there's no overlap between our signals. Okay, we could get some overlap, meaning part of our signal is overlapping and some is not. Okay, we could get complete overlap where they're completely enveloped in each other. Okay, so these are kind of things we want to keep looking out for, because it'll be important later. Okay. Okay, so this is going to be our h of t minus tau at 3, and here is our initial x of tau. Okay, so here are some possible scenarios I've listed. Which one of these would you guys classify this situation in? So right now we've shifted h of t minus tau so far to the left that everywhere that x of tau is non-zero, h of t minus tau is 0, right? So I'll repeat that one more time. Yep, no overlap, perfect. Every time where x of tau is non-zero, h of t minus tau is 0, and the opposite is over here, right? The only time where h of t minus tau is non-zero, h of t minus tau, x of tau is 0, right? So here's the no overlap situation. So then, if you guys remember, we're now going to slowly move this over and over and over until there's partial overlap, full overlap, partial, and no. So little spoiler, but there's going to be a total of 5, right? So we're going to have no overlap, some overlap, then it'll be completely enveloped. Then once again, partial overlap, and then no overlap. So we have to draw these 5 scenarios so we can define functions for each of these 5, okay? So now let's draw the scenario where there's partial overlap on this left side, like I just showed. Okay. And let's keep track of the conclusion from this. So the conclusion from this was that there was no overlap. Okay. So now let's shift this over. We're going to something like this. And somebody just entered the waiting room. I'll let them in. Okay, so now we're going to get something like this, where there is, actually better to draw it like this. There's going to be partial overlap. Okay. So here is going to be the region we care about, right? There's some overlap right there. So we're going to look to find the area of that region. Okay, so here we have partial overlap. Okay. And now let's draw the full overlap condition. Going to look something like this. Right? So now it's going to be completely overlapping. And let's finish up strong and draw the last two scenarios. Okay, so we're going to keep moving it from left to right until we go from full overlap to partial overlap and then no overlap at all. And while I'm drawing these, are there any questions at all? Any doubts or confusions?
Why are we like overlapping it like this?
So the reason we're doing this is because it's a continuous function, right? So
Right.
yeah, I prefer not to explain it into super great detail, but the reason we're doing it is because we're trying to find overall functions to represent that overlap, right? So we're trying to find continuous functions based on our integration that represent that overlap. If we were to do, for example, discrete convolution, then it looks more like you have a bunch of points, right?
Mhm.
And then you have another set of points. Right? And you take these points and you start from all the way left to right, and then you basically find the dot product. So you multiply all these together. So this is multiplied by 0, 0, 0, 0, multiply this, and you, without getting into too much detail, you're going to move all these points from left to right, and then continuously multiply them. So you multiply these three, and you take that multiplication. So we have three numbers here, multiply them, and you add them, and then you get a new point, right? So that's like discrete convolution. And I really don't want to confuse you because that's a little bit later on that you'll learn. But basically, just keep in mind that the reason we're even doing convolution is because we have two signals and we're trying to find how similar they are, right? That's the whole key. Trying to find the mapping of one onto the other. And the reason we're finding the overlap is because we have to be able to find functions that represent that overlap. So because whether or not it's based on no overlap, partial, or full overlap, based on whether or not they fit these three criteria will affect how we take the integral. And we need to be able to find like, yeah, the overlap to be able to get some continuous function to represent that overlap. Does that make sense?
Okay, so yes, but we're doing the partial overlapping. Is that kind of just arbitrary? Like it doesn't really matter how much of it is partial or like how much of it is actually overlapping?
Well, it'll be partial until we get to this point, right? Where like once we get to around here is when it'll switch from partial to full. So I want to say no, because you go from no overlap to partial, and then we treat this whole condition right here. So partial, 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 partial. That's all like one condition, and we account for that in the integral. In the condition, we like treat it as like a piecewise function. So we'll get to it a little later, but the width of this is 1, right? So we know that from here, it's going to be no overlapping. So this would be a shift of 0, right? And then a shift of -1 gets us over here, right? So we know that from in between 0 and 1 will give us that partial overlap. So we'll take a piecewise function for that.
Okay,
Does
and
that make
then
sense or no?
yeah, it does. You don't really care about the actual like amplitude. It's just like if the T part is covered, like since there's like that region that goes from 2 to 3 for like the blue function, like you don't really care about that for like a full overlap.
No, we don't care about it. We don't care about it.
Oh, okay.
Because it's only
Thank
the
you.
mapping of one onto the other. Yeah, yep. And we'll account for that in the integral. And you'll see a little later. But once we get all of our regions out, then we'll care about the amplitude. But for now, it's just yeah, overlapping, I guess, on the time axis. If that makes sense. So even if Yeah, the amplitude would be irrelevant, specifically when we're talking about when it's overlapping, partially, fully, or not. Does that make sense, guys?
Yes.
Yeah, because you're saying like you're taking the like or when you're talking about the discrete, you're saying taking the dot product, right? So that's more or less just like projecting it onto
Yep.
the other signal.
Exactly.
Okay.
Jade, you're back to A+ student. I'm sorry, Eddie. You're out of here.
Yeah, so
that
like
was
are we just going through kind of like a visual representation of what like convolution would be doing in terms of
you'll
the
actually,
math?
I think, yeah, we're gonna play a video a little bit later. This is one of the easier problems. So we wanted to show you a problem first and then the video. But there's some really great resources online, so I'd highly recommend taking advantage of that and looking at videos because there's some amazing visualizations. But yeah, basically, in like layman's terms, you're just taking a moving average and then you're trying to find a projection of one signal onto the other. But in extremely big picture terms, you're just trying to find the similarity between two signals. Is the essence of convolution. Okay. Everyone feeling good? I have my gallon of water with me today. You guys thirsty? Let's stay hydrated, guys. Okay, let's move on. So here we have full overlap. And I don't want to rush for this next portion, but I think Ryan has a much more interesting problem that will be a little bit more relevant because this is a little bit on the basic side. So I'm gonna breeze through this a little bit, but please interrupt me if you guys are lost, okay? Or I'm going too fast, or anything, any doubts. Okay. So here, once again, we have that partial overlap. And then here's no overlap. Okay. Everybody feeling good? Okay, so now we have completely defined the regions all the way from the left, from the left when there was no overlap, all the way to when there was on the right with no overlap. So that'll completely encompass everything, all possible regions where there's something interesting going on. So now we can define the actual integrals. Okay. So let's start here. So let's say for t less than 0, right? So now for t less than 0, we're in this region, right? Because keep in mind, it gets a little tricky because we're switching between tau and t, but tau here is our dummy variable. T is the variable that's determines determines left or right, how far we're shifting, right? So when we change t, determines where our kernel, this h of t minus tau, is on the graph in terms of shifting left or right, okay? Okay. So yeah, going back to this. So for t less than 0, there's going to be no overlap. So we can confidently say y of t equals x of t times h of t minus, or x of t convoluted with h of t, which, if you remember, is the same as this, right? Is going to be equal to 0. I guess it's not true, but yeah, equals to 0. Okay. And if we were going to integrate it, we could just define the limits from negative infinity to 0, but it's just, yeah, I think it's being a little bit too over dramatic, but we know it's equal to 0 because there's no overlapping regions. We feel good about that. And now let's go into the next region. For 0 less than t less than 1. Okay, this is our next interval. Now, this is going to be our partial overlap interval. And you may be wondering, how did I get this 0 to t less than 1? I was kind of alluding to it earlier. when I was talking with Isabella. But here we see that the width of this is 1, right? So this h of t minus tau is going to be partially overlapping from when this right guy is greater than this. So we have, yeah, a value that's less than 0, right? Because this here, the more we, I'm gonna explain this. Once this right corner begins to cross here is when there will be overlap. And because the width of this is 1, we know that between 0 and 1, we'll shift the h of t minus tau in a way that they'll be partially overlapping. If we're less than that interval, so we're t less than 0, there's going to be no overlap. And if it's t greater than 1, there'll be full overlap. So 0 to 1 is that region where there's partially overlapping, and we know that because of the width of h of t minus tau. Okay. Okay, so here, once again, we're going to say y of t is equal to x of t divided with h of t. And this is going to be equal to infinity to infinity. Tau, right? So this is the overall formula. But based on our actual intervals, we can say this is equal from 0 to t, right? For x of tau times h of t minus tau, d tau. And then we can say here, to t, 2 times 3. How did I get this? This was the amplitude of our kernel. And this was amplitude of our signal. Right? Okay, and then we're going to integrate d tau, which gives us 6 tau from 0 to t, which is equal to 6t. Okay, so I know that might have been a little confusing. Does anybody have any questions? What this 6t means here is this is going to represent the overlap when there's only partial overlap between our kernel and our signal, okay? Okay, so before I keep on integrating, can I get some thumbs up that actually made some sense? You guys understand how I got this? Any questions for anything?
So the result that you get is 6t. Is that because convolution is basically showing how similar they are, that means that 6t is representing, like, as you move the kernel, it increases linearly in similarity to that signal?
Exactly, Jade. You're going to become our signals prodigy, all of you in here. That was excellent. Yeah, so as you shift it more to the right, it'll increase in similarity, right? Because there's going to be more overlap. So does that make sense?
Yeah, that does. Okay.
Whether or not you change t will affect the shifting of the kernel on the graph. And then the larger you go, the more overlap. And this just happens to be a linear relationship because both of their amplitudes don't change in time. Everybody makes sense to everybody? Megan, Ruhi, 80. Yeah. You guys alive? Or did I kill you with signals? Okay, Ruhi's alive. Okay. Somebody do CPR on the rest of the people while I'm finishing this up. If you guys are still alive by the end of this. Okay. So now we're going to go from 1 to t to 2. So once again, how did I get this? And that's why it's important to draw this, guys, is because drawing it is how you're able to figure out which intervals to choose. So here, this is going to be our full overlap situation, right? Because from values of 1 to 2, the kernel is fully in the signal. But once we get less than 1, we have partial overlap. Once we get greater than 2, we're back into partial overlap again, right? Based on this. Okay. So we know that this is full overlap. So then you can say, so I'm just kind of skipping this step. I'm just starting off with the integral. We're going to integrate from t minus 1 to t. Once again, these are the amplitudes for our signal and our kernel. So here's where those amplitudes come into play. Once again. Okay. So we're going to plug these into here. Okay. So we're getting a constant, guys. Why are we getting a constant? Let's try to think about this.
Because it can't get like any more overlap. Like once it's fully overlapped, it doesn't like get more overlapped.
Perfect. Yeah. No matter where we shift it in that range, it's going to be the same value either way, right? There's no more you can overlap it because these values aren't changing in time. If we had something like, you know, if in that same region it was something like this and they're changing, it definitely wouldn't be a constant, but because they're both staying constant in time, there's no more overlap left or right. There's only so much you can overlap. And it's the same no matter where you shift it. Excellent answer, Isabella. You're now at our A+ student, Jade. You're in second place. Okay, so here's 6. Now let's go back to our partial overlap condition. This is gonna be our last one. So bear with me, guys. Well, second to last, but the last one's really easy, just 0. We're going to this region. So once again, how did I choose this? 2 less than 3. It's gonna be this partial overlap, right? When we're less than 2, we're gonna be fully overlapping. When we're less than, or when we're more than 3, there's gonna be no overlap, okay? Okay, so once again, we can set our integral bounds. Okay, now we're gonna plug this in here. Okay, guys, there's 2 questions I have for you before we move on. We're pretty much done here. But the first question is, we're getting a negative 60 for the value that's for our slope here for this, determining our similarity between 2 and 3. Why is this negative 60 and why is this positive 60? Why are they flipping signs? Why is one positive and one's negative, guys? Let's just get some like intuition for how convolution works.
It decreases as you like get less. Since we start with the full overlap, once we keep moving to the right, we turn into like a partial overlap.
Yeah, beautiful answer as well. You're gonna stay at the A+ for a while if Jade doesn't pick up the pace. I'm just joking. So here, guys, when we're increasing t, we get more overlap, right? We're shifting it more to the right, so there's gonna be more overlap. But here, if we keep increasing t, we're reducing our overlap because we're getting farther away, right? That's why it's negative. Okay, so for the last part, we're gonna have for t less t greater than 3, and we're going to have, once again, just equals 0, because there's no overlap. Okay, so now we've done all these different segments, guys. We've done all these different segments. Now we're gonna wrap up our answer, okay? So we can now define this as some piecewise function based on the interval, right? And your first instinct might be to add them, but that doesn't really necessarily make sense, right? Because based on where you are in time will affect the corresponding convolutional, the corresponding value of overlap, right? So we're going to find it as a piecewise function. Okay, any questions, guys? We can also plot it if we want. So remember how I said before, we have two signals, right? Our signal and our kernel, and then we convolute our kernel with our signal to see the similarity. So we can now plot this and see the corresponding result of our convolution. So how similar these signals are over time, right?
Why do we end up with like an 18 for like the 2 to 3? Like why doesn't it start like around 6? Like just because.
I think it's because you're always going to have some portion of, like, if you want to start here. So as we keep sliding it from the left to the right, right now there's no overlap, right? So it's 0. And then we're continuously adding. We're adding the overlap, more overlap, more overlap, more overlap. But here, we've got maximum overlap. So we're already starting from some plus value. There is some overlap. And as we increase t, we were removing that overlap. Does that make sense? So here there's maximum overlap. And as we increase t, we have to remove some of that overlap, some of the similarity.
Right.
Does that make sense? So the 18 is kind of like the maximum there.
So why isn't the constant 18? Why is it 6 then?
Why isn't the constant 18?
It's like 18 is the maximum that we like initially start with when we're transforming from like the maximum overlap or like the full overlap to partial overlap. Why is it just a constant 6 then when we have like the full overlap?
That's a great question. Let me think about it for a second.
Does it have anything to do with the bounds of the integral that you chose for that?
I think you're on the money there, Jade. I think so.
Because I'm trying to
double
figure
check the
out
answer
why
for
you specifically chose those bounds for integration as opposed to like, I don't know, like 2/3 or something. I don't know.
Well, I think we chose, so the reason we chose t minus 1 and t is because, like, within here, see, yeah, this might be better. Within here, it could be, any variable, but we have to like ensure that the width is still 1. So we can't really have a constant here. So the bounds for that makes sense because as long as it's within the range of the signal in terms of it'll definitely be fully overlapping, and we just have to ensure that the width is always 1. So that's why we have t and t minus 1. So as long as we're in that time range and our width is 1, we're all good. But for this one, we chose 2 and t minus 1. So the reason we chose 2 is because that's when this ends, right? I probably should have gone over that. Thanks for bringing that up, guys. The reason we chose 2 is because that's where this ends. So once we go past 2, then x of tau becomes 0. That's bad news. Right?
And why do we choose t minus 1 for the other bound as opposed to like 0 for where it doesn't? Or
because that'll give us this other corner. So the width still has to well, wait, actually that doesn't make sense. T minus 1. Let's see.
Are you talking about for the last part or the partial overlap?
Yeah, why did we choose T minus 1 for this bounds again? Look at the
Because
answer.
T minus 1 represents the left side of the like block in your H of
Oh,
tau
yeah.
equation.
Yep.
So you're basically integrating from the left side of that block up until 2, which is where your X of tau function becomes 0.
Right, and
Yep.
then because you're changing
Yeah.
like T as you go. Okay,
Mhm.
I got
Does
you.
that make sense?
Yeah. So because that bound is actually what's changing. So yeah, that's why I have to put the variable T in there to begin with because it's changing.
Yeah.
Okay. I
Yes,
gotcha.
exactly. Because your T and your T minus 1 represents the bounds of in this case, it's basically a block. So it represents the vertical sides of the block as you sweep it across the other function.
Gotcha.
And then to answer your initial question, Isabel, about why it's 18, still not 100% sure, but since we know that, I mean, this is not decreasing. I mean, I think it's just 18 because of the rate that this is decreasing. It's just kind of like how the math works out. So every time point, we lose an area of 6, right? Which makes sense because the overall overlapping region here is 6. So if we increase by 1, we lose that 6. But I'm not 100% sure about the 18. So if any of the other TAs have any
Are you
ideas?
talking about the y-intercept there, the 18?
Yeah, just getting some intuition for that.
So when t equal to 3 for this specific part of the function, if it's 60, it's just going to remain like, 18. And if it's just minus 60, it's going to end up in negative axis of minus 18. So when you offset it with like 18, your signal is going to just end up at the 0 axis. So when t equal to 3, you're essentially just getting a 0. And I think this is like the intercept or offset that, that the signal needs to like follow the pattern of the other side.
Yeah, great point.
Yeah.
Great point.
Like
so here,
the
if we
rate
actually plug
at
in the
which
bounds,
it's
yeah.
like increasing, it should also be like decreasing at the same rate. So yeah.
And this is the area of the overlapping.
Yeah.
And this is when we have no overlap. Right? Because we're just plugging this into there. Does that make sense?
Yeah, so when we go back to the graph of convolution, like now where they interact, but with the piecewise function.
Yeah.
Okay, never mind. Okay, I get it. Okay, thank you.
Are you still confused? I mean, we're happy to have.
No,
you know.
I understand now.
So it's just because of the
yeah, the offset
bounds
works
of the
out.
time that like, we get this, like we get to like this equation 18 minus 60. If it was
Right.
different bounds, we would have like a different equation altogether. So essentially it's all just math, just doing its way.
I get it now. Thank you.
Yeah, thanks for hopping in, Ryan. and Nina. Okay, guys, that's all for me. But do we have any other questions? So, I went way over time, but I hope that helps somehow. Okay, can I get a see a thumbs up, and I'll pass it to the next person.
Could you just show the final plot again, real quick?
Yeah.
I'm gonna take a screenie of that one.
I'm also I'm gonna put
All
on,
the
put on Canvas.
Oh,
Yeah, all the
true,
work
yeah.
gets put
It's
on-
okay.
puts
I
on
just need to
Canvas.
like transcribe it really quick. It's okay. Yeah.
Oh, wait, I messed up. Wait, redo the
Oh,
screen.
shoot. Okay, hold on.
Redo the screen.
Okay, done. Thank you.
All right, thanks, guys.
Thanks, Bill, for your great explanation. Hi, everyone. Thank you for still coming to recitation tonight. Good job surviving from your exam. Okay, so I'm gonna start taking after Will. But first I have a video to show you guys. Go here. Let's see the video first, shall we? All right. So Will and Ryan recommend us to show you this video because it's a very great resource, and I think I watched this video and I think it's gonna really benefit you. And also this channel, they don't only offer only this content about signal and system and not only with convolution, so they offer a lot of content that you can check out. I think it's really made. Definitely will be useful for you. Okay, so let's watch it.
Suppose I give you two different lists of numbers, or maybe two different functions, and I ask you to think of all the ways you might combine those two lists to get a new list of numbers, or combine the two functions to get a new function. Maybe one simple way that comes to mind is to simply add them together term by term. Likewise, with the functions, you can add all the corresponding outputs. In a similar vein, you could also multiply the two lists term by term and do the same thing with the functions. But there's another kind of combination just as fundamental as both of those, but a lot less commonly discussed, known as a convolution. But unlike the previous two cases,
Or it seems like
it's
we
not
short
something
in
that
time. Wait,
Do you want to
Amulia?
just really quick, you go to like, just scroll a little farther, maybe to like minute 8. Keep going, keep going, keep going. That one. Yeah, right there.
This.
Yep, halfway through, right there.
Okay,
Stop.
let's watch this part then.
2 times speed. No
average.
volume.
Imagine you have some long list of numbers, and you take another smaller list of numbers that all add up to 1. In this case, I just have a little list of 5 values, and they're all equal to 1/5. Then if we do this sliding window convolution process and kind of close our eyes and sweep under the rug what happens at the very beginning of it, once our smaller list of values entirely overlaps with the bigger one, think about what each term in this convolution really means. At each iteration, what you're doing is multiplying each of the values from your data by 1/5 and adding them all together, which is to say, you're taking an average of your data inside this little window. Overall, the process gives you a smoothed out version of the original data. And you could modify this starting with a different little list of numbers. And as long as that little list all adds up to 1, you can still interpret it as a moving average. In the example shown here, that moving average would be giving more weight towards the central value. This also results in a smoothed out version of the data. If you do kind of a two-dimensional analog of this,
All right. Okay, let's see the chat. Yeah, like Will said, this is the example of discrete convolution. So the method for our example tonight, continuous convolution, is gonna be similar. And let's see what example we have in our recitation tonight. Okay, so for continuous convolution, the way that we solve this is gonna be similar to what we just solved recently. However, we're gonna replace t with dummy variable tau. And we're gonna have to do some operation on h tau here. So we're gonna just start to reflect it and shift it. And also we're gonna put the signal that we flip and shift here into this part, which is our convolution equation. All right. Now let's see example that we have on our recitation here. Okay, given the signal xt and ht, let's compute the convolution of these two functions. So the first step that is very helpful, and I feel like you must do this maybe a little bit in your head, or if you have the chance to write it out, you should always draw your signal. Because why? Because when I took this class, I only remember the shape of graph that's being used in the class, but when I have to like do the real exam, it's changed into another kind of graph instead. That's why it's very important for you to know how to draw the signal. All right. Okay, let's draw the signal together. Anyone would like to try on this? Or actually, I'll give you a head start so we can go over this quickly here. Okay, let's look at this. So I have a lot of Discord, is it? Excuse me? Wait, excuse me, TA, is that from Discord, TA? Do you
Yeah.
want
Yeah,
me
sorry.
something?
I don't think they realized it was cut off there.
Oh, I
You're,
see.
you're all good.
Yeah, I'm okay, and I'm not sure how to mute this. Okay, let's continue. But if you have anything that you want to comment or let me know, feel free to like talk here on Zoom. Cool.
Absolutely.
Okay. First step, draw signal. So this part, right? Every x that we have is going to be correspondent to t. So if we have t as 1, our xt is going to be 1, 2. If we have our xt, if we have t as 2, xt is going to be 2. And also as 3. And it's only up to 3. But after we have like t that's like more than 3, and actually between 3 and 6, our signal is not going to be the same way, not in the same pattern. So let's say at this point, we have t equal 4, right? Can anyone tell me what's gonna be the xt here? Feel free to annotate. I feel like we have annotate function available here. Thank you, Isabella. Yes, it's gonna be 4, right? Because t is 4 and 6 minus 4 is 2. The same trend as 5, and otherwise 6 is 0 and also 0 is 0. So our signal here is gonna look like a triangle graph here. Okay, it's gonna look something like this. Now, let's try this graph, shall we, for ht? So it's 2 of ut minus 1, right? Do you remember our step function ut? Normally, it's gonna look like this, right? This is 0, and this is 1, and this is normal ut. So, okay, do you remember signal transformation? We start from time shifting property first, right? Yeah, we start with like stuff on in the bracket first, and then we do outside later. So anyone would want to try to like write this signal down on this graph? Thank you, AD. Okay, yes, that's correct. It's gonna start at 1, right? Because you have the right to be negative. Therefore, you shift it to the right by 1 unit. And because you have 2 as amplitude here, you're gonna, yeah, it's gonna be, instead of being 1, the amplitude is gonna be at 2 here. All right. However, you remember the first step of solving this problem on this page? Instead of using just normal t, we can now replace it with dummy variable tau. And how are we doing that? Do you want to take a guess? Yes, we just changed t to tau, like just like this. So CL graph used to be t here, right? We just changed it to tau. Our t here also changed to tau too. But the shape of signal is gonna be the same. And that's the first step after we draw our graph. All right. And the second step is to shift and flip, like as we see here. Even though it's like flip and shift here, it is preferable to do shift and flip. And how are we doing that? Let's see. Oh. So first we shift this h tau by t unit first. And you know you have the right to be negative, right? But it's gonna look like this. Our graph is gonna look like this. So instead of like being at 1, now your function is gonna be at 1 minus t. And after shifting, you want to flip this signal. And this is what you're gonna get after you flip the signal. Remember this shape, okay? All right. And the next step, after we have the signal, that's we transform it by using the dummy variable and using shift and flip on h tau here. We're gonna have to consider the overlapping scenario, like Will has shown us. There's gonna be no overlap, some overlap, and full overlap. So let's start at the first scenario here. So first scenario, there's gonna be no overlap at all, no overlap, as you can see on this graph here. So this is t minus tau. And this is x tau. And we want to find, when we do convolution, we want to find the area of the under the graph that it overlaps together, right? But because this case, there's no overlap between these two signals. Therefore, can you guess what is the convolution is gonna be? You can write down on annotation, or you can just speak it out loud to me. Thank you, Jade. It's gonna be 0. You rock it. Thank you so much. Okay, so in this scenario where there's no overlap, the convolution of the two signals here is gonna be 0. Now let's look at this case 2, some overlap. So as you can see here, my graph hasn't been overlapped yet. And I'm gonna just show you in this case, how should we move our signal? Okay, I'm gonna move my signal. Now you see there's some overlapping regions, right? Yeah, now there's more area that's being overlapping together. And I'm gonna just stop right here. And why do I stop right here? That's because I only want my h tau to stay in this region of x tau. Does not change the equation yet. Like this part is t, right? But after that, it's gonna be 6 minus t. And I don't want that just yet. I just want to consider it portion by portion first. And now, we need to take a careful look at the boundary condition here. Like you see on the first example, first case scenario, that I specify the the boundary of t, right? Now, do you want to help me identify what is gonna be our new boundary condition here? I'll give you a hint. So we're gonna look where the signal start overlap and when it ends. But see, if I move this, no matter like if I move this, it's still overlap, right? And if I move this here, you might think that the boundary is gonna be at 1, but no, it's actually not. We don't know where it is yet. So we're just gonna say for this scenario at t minus 1 is still gonna be less than 3. Less than 3. While also we're gonna have t minus 1 more than what, everyone? You wanna put your answer here? Okay, I help you with this one. It's gonna be more than 0. Here, we need to pay attention to boundary condition. And if I write these down, we're gonna have boundary condition where t is less than 4 and when t is more than 1, right? And I will write my condition here so we can see it. Now, in this case too, our graph is gonna look something like this. Okay, now let's calculate the convolution of this scenario. Okay, from convolution equation, and as I say, pay attention to the boundary condition. So we start the overlapping area at 0 and then with t minus 1. Therefore, our boundary condition is going to be at 0, from 0 to t minus 1. And remember, x tau is tau, and ht is going to be 2 dt, right? Therefore, if we solve this equation, we're gonna get this equation as like the area under the graph in this scenario. And we're gonna mark this answer and we're gonna save it for later. Anyone have question or you confused about this step, why I'm doing this here? Do you want me to go over it? Or you think you're good for this part now? If you're good, please give me a thumbs up. Why do I stop at 4? Because at our boundary condition, right? I want to stop my graph before it changed from when is t. You remember xt is t until after t equal t, then equation of the graph is gonna be 6 minus t, right? And I only want to consider this scenario first, where the convolution, the overlapping is still within t when the graph equation is t and not 6 minus t yet. We are gonna talk about that later, but for this scenario, we just pay attention to t minus 1 stop before t. And it stopped before t, therefore t is less than 4. So is convolution only going to with piecewise function? Is convolution only going to with piecewise function? I'm sorry, Adia, I don't quite understand your piecewise function. Wait, I'm not sure how to answer your question here. Any TAs have idea for Adie's questions?
Are you asking if you can only use it with piecewise functions, or are you asking if it only gives you piecewise functions?
If you could only do convolution when it gives you piecewise functions.
So you would be able to do a full convolution, but I don't think that is particularly relevant to this class. In general, you're going to be getting piecewise functions.
Okay.
Because think about
Thank
like the real world scenario of this is you have two signals, and in the real world, you're never going to have an infinitely long signal. So
Yeah. Okay, thank you.
absolutely.
Thank you, Ryan. Okay, are you good with this part now? Give me thumbs up if you feel comfortable to move on. Okay, thank you, Ruhi. Now let's look at the next scenario. Like, okay, first we talk about when we want our ht minus tau to stop right before 3, right? Now we want the area of overlapping to also cover this part too. So our graph now, we pass the t, and now we enter the 6 minus t. But I'm gonna stop here just before 6. And why is that so? Because if I move it past 6, it's gonna be full overlap. It's gonna be full overlap scenario, and I don't want that. I just want it to be still some overlap case. Okay. All right. Anyone would like to try me with the boundary condition here? Anyone would like to try to help me? That's correct, Isabella. Yes, it's gonna be t minus 1. It's gonna be less than 6, right? But it's still more than 3. Thank you so much. You aced this. Okay, now let's do calculation for t, right? So if t minus 1 is less than 6, that means t is less than 7. And when t minus 1 is more than 3, it means that t is more than 4. So in the end, we'll get t is more than 4, but it's still less than 7. And yeah, we still need to remember this boundary condition. All right. Now, after we know how our graph looks like, okay, remember our convolution equation? Now, the highlight part is going to be whether if you can correctly identify the boundary condition when you actually put it into the integration. So here, remember t, this part, right? It's going to be when t is less than 3, it's just going to be t, right? And we change our t into tau. So the equation of the graph here is going to be tau. And after that, our equation is going to be 6 minus tau, right? Because it used to be 6 minus t. Now, let's observe the boundary condition here. Do you understand why I said the boundary condition as 0 and 3 for the part before tau equal 3 here? And why do we set it as 3 to t minus 1 after tau is more than 3? So yeah, just like the previous case that we just look at it, we want to focus on the start and the end of overlapping area. But instead of looking it at one piece, like case 2, we now looking it as 2 pieces because we now have like 2 regions that don't have the same equation anymore. Okay. Are you good with this part, everyone? You have any question on this part? Okay, cool. I will move on. So after we solve our integration, the final answer that we will get for this part, this scenario of overlapping is gonna be this following. So mark that down. And we're gonna look at the last scenario here, full overlap. Anyone would like to help me try? Putting the boundary condition here, full overlap. Actually, yeah, let's make it longer. So it's fully overlap. Right? This is gonna be t minus 1. So in this case, right, we don't know where it actually start now for convolution, but we know where it's gonna end. So in this case, we know for sure that t minus 1 is more than 6, right? Therefore, we know for sure that t minus 1 is more than 6. Therefore, our t
Did we lose alpha?
Yeah, looks like it.
No, what happened?
I think the power cut happened at her place and not your place.
I'm guessing that might be the case. Do we? Oh, she's back.
I got kicked out of Zoom. I'll come back. I am back now.
Okay, you're all good.
Wait, where I got cut off now? The full overlap part.
Yeah.
Okay, cool. Let's resume from that. We're just a little bit. We're near the end now, everyone, for tonight. Okay, can you allow me to share screen, please? It said host to support participant screen sharing. Hello, hello. Yeah, I still cannot share my screen.
Do you want me to share my screen and you just try to like write the remaining part out?
Try it now, alpha.
Okay. Thank you. All right. Okay, let's get back to this.
Yeah.
We're in the last part now, everyone. Okay, now after we know how our graph is gonna look like, let's solve for the convolution. Cool. Remember our convolution equation? Oh wait, why does it trigger whiteboard here? I want to share my screen, please.
Try sharing it now, it should work.
You cannot start screen sharing while collaborating on whiteboard. Yeah, there's someone opened the whiteboard, that's not me, so you have to close it for me to continue. Okay, cool. Thank you. Okay. Okay, and it's like the previous scenario, right? We have two pieces that we want to solve. So the piece before 3 and the piece after 3. However, the thing that's gonna change, because in this overlapping case, scenario used to be that t minus 1 used to be boundary condition, but now the thing on the edge is not t minus 1 anymore. Things on the edge of convolution is gonna be 6 instead. That's why we change our boundary condition from t minus 1 into 6. And we're gonna solve the equation just like we did in the last previous cases. And we're gonna get a whole number here. After we solve everything, we're gonna get yt equal 18. And do you remember what Will mentioned? Why the full overlapping case is gonna be just whole number like this and no more variable t anymore? Yeah, it's gonna be the same thing as Will said, because now it's only fully overlap. No matter how long we're gonna move it further, it's gonna be the same overlapping area of convolution. That's why it's gonna remain the same number. Now, when you answer this question, you need to put in everything together. So let's see our first scenario here. What is our equation? Oh, it's 0. It used to be 0 there. So yt for t that is less than 1 is going to be 0. And when we look at case 2, when t is between 1 and 4, our yt is going to be this equation, right? T squared minus 2t plus 1. I'm going to put that in here. And another case, when t is between 4 and 7, you're going to get negative t squared plus 14t minus 31, right? So I'm putting that down. 14t. Okay. Just want to make sure I did the right copying here. Cool. And in our last scenario, we get yt equal 18.
Okay.
And then we're done after we put everything together.
We're going to the gym. No, Mel is not back. Oh, you and Alexia.
Amelia, you're unmuted.
Oh, shoot. I'm sorry.
All right. Anyone has questions? Do you want me to go over any part again? Question, comment, concern?
So for the last integral, we basically just converted the boundary from t minus 1 to just a constant value 6, because no matter like how far we push the boundary anymore, it's not going to change. So we just give it a constant value to make it easier.
It's because look at this overlapping area, right? The boundary is not t minus 1 anymore. The boundary of this overlapping area is going to be from 0 to 6.
Okay, gotcha.
Yeah, and that's it. But you got to be careful when you move the graph together. This made me confused too when I do this type of question. So you better practice and determine the right boundary condition that you're gonna use in your graph and when you do the integral. Coolio. Oh, okay. Anyone got more question, comment, and concern? All right, and I believe I'm gonna pass this on to Ryan then.
Okay, so I real quick just want to say the biggest thing with convolution problems is practice. So if you practice them, you'll get a general feel for like just intuitively like, oh, this is going to be my bound here for partial overlap, and then this is going to be my bound for full overlap, and you'll get a lot more comfortable doing that. So just make sure that you are solving all of the homework problems and going back and maybe solving these recitation problems again before the exam. Because the more practice you have with that, the more comfortable with it you'll get, and the less likely you are to make a mistake. This is a pretty challenging concept, so definitely practice it. And we do have a third problem. I am actually just going to introduce it real quick. And then if y'all want to try to solve it over the following week, y'all are welcome to. I would recommend it. And then I will solve it at the beginning of next recitation. So let me real quick share my screen. Okay. So this is the problem. Take a picture of it or write it down or something quick if you want to give it a shot on your own over the coming week. And I will give you a short introduction into the problem before we go, and y'all can try to solve it on your own. So let me know in chat or just give me a thumbs up whenever y'all are good. You got it written down and everything. I'm gonna move on. Take a screenshot or a picture of it with your phone or something quick. So the first step. Oh, if my iPad will work. Why is it not letting me write? Oh, I think my iPad is frozen. Why is it not working? Sorry, give me just one moment. My pencil die. Ah, that is the problem. Okay. Able to draw with my finger? I am not. Okay, we're gonna jump over to whiteboard real quick because my pencil died. Just a moment. Okay, is everybody able to see? All right, so we have our x of t, and I am not good with writing with a mouse, so I apologize, is equal to sine of t u of t. God, this is rough. H of t is equal to e to the minus 3 t u of t. And now y'all see why I always use my iPad. So we want to calculate the convolution y of t is equal to x of t convolved with h of t. So step 1, we want to graph our x of t and our h of t to get an understanding of what the signals look like. So let's do that quick. So we have sine of t times u of t as our x of t function. So u of t means that it's going to be 0 for everything before 0. And then it's going to turn on at 0. And then it's going to be multiplied by our sine function. So we're just going to get our sine function out after 0. So we have t is less than 0, x of t is equal to 0. And at t greater than 0, x of t is equal to sine of t. Now for our h of t, it's equal to e to the minus 3 times u of t. So once again, we're going to have 0 before 0. And then it's going to become e to the minus 3, which is going to look something like this. It's not super important you have exact values, just an idea of what the function is going to look like. So now we're going to go to step 2. Replace t with our dummy variable, tau. So we get x of tau and h of tau. And that is going to look the same when we graph, except this axis is now going to be tau instead of t. So this is now tau, this is now tau, and this is now tau up here as well. And then our third step, Our third step, we need to shift and reflect our h of t. So we're going to get h of t minus tau, which is going to make our function h of t, or h of tau. We're going to shift it by t, and we're going to reflect it across the y-axis. We're going to do a time reversal. So we're going to get something that looks like this. So now we need to consider regions of overlap. So whenever t, so these are our two functions, right? This is our x of tau, and this is our h of t minus tau. So as we can see here, whenever this t value is less than 0, oh, I'm sorry, are y'all all following this correctly? Okay. Is everybody following me now? I should have made everybody follow me. Let me know if y'all can't see or are not able to keep up. I'll pause and make sure everybody's on the same page. but okay. So we can see that when t is less than 0, these two functions are never going to overlap. Because this function is always 0 here. Well, I guess they overlap, but this function is always 0, which means that our y of t is going to be equal to 0. Oh God, I butchered it. So we can see that t less than 0, there's going to be no overlap. Y of t is going to be equal to 0. And we can see that when t is greater than 0, we're going to have overlap. And in theory, the only place we can have full overlap is at infinity. So we can treat this as our final case. In this case, we only need 2 cases because once they overlap, they never stop overlapping. You are permanently at a state of partial overlap unless you go all the way to infinity. So when t is greater than 0, what is y of t equal to? That is the question that we need to answer. So we know our convolution equation. Y of t is equal to integral from negative infinity to infinity x of tau h of t minus tau integrated with respect to tau. So in this form, we're going to get y of t is equal to integral from negative infinity, positive infinity, and our x of t is sine of t, u of t, and our h of t minus tau is going to be equal to e to the negative 3 t minus tau u of t minus tau d tau. Let me double check that this is right. I don't want to send y'all on a wild goose chase doing the homework. Or not the homework, sorry. I shouldn't say the homework. I would recommend you give this a try though, because this is going to be more similar to problems that you likely see on your homework in your exam. This problem is a bit more difficult than the other two we've gone over. So this is correct. And the things you need to consider here is what does this do to your bounds? So I will do this step for you, and then I will leave it to y'all. So because we have a u of t multiplied by our sine of t term, it means that this region is going to be always equal to 0, which is what we said over here. That means everything before that, we don't need to integrate. So we can put a 0 as our bottom term on the integral. Now this term over here, our u of t minus tau, means that whenever we're integrating, we're stopping at this point, because this is your t value. Your t minus u of t minus tau represents this vertical line here. After that, we no longer have overlap. So we only need to integrate this area in between these two regions. So we can replace the top bound with t. So now we are only integrating from 0 to t. And we can remove those step functions from the equation as we factored them in to our bounds. Oh, I apologize. I think I wrote t minus t up there. This should be a t minus tau. So this is where I will leave y'all. And you guys are welcome to give this a try over the coming week before our next recitation. I will say, in order to solve this problem, you will need to use Euler's formula, which I believe we talked about in the first recitation. But as a reminder, sine is going to be equal to, let me make sure I don't mess this up, e to the jt, where j is equal to I. Just to be clear, e is equal to jt minus e to the negative jt divided by 2j. And cosine is equal to e to the jt plus e to the minus jt divided by 2. So you will need to know those two. Oh, I made the same mistake up here. I'm sorry. You'll need to know these two identities to solve this problem. So make sure you write them down or take a picture of it. And then I also made a mistake up here. The sine of t should be tau, and this u of t should be tau as well. Apologies. Sine of tau, u of tau, sine of tau, d tau. All right. I will leave y'all with that. I will leave this up on the screen. So if you want to take a picture of it or anything, give it a go. You're welcome to try. And we'll pick up here at the start of next recitation. Anybody have any questions about anything we've gone over today?
I do have one final question.
Yep.
So, is there a specific reason why we chose T for like the leading edge of the kernel signal as opposed to, because like the previous one we did T minus 1? Is there like a reason why they're not the same, or?
So generally, whenever you have, so basically the reason is because this side of this function is not bounded. This, in theory, has a, what do you call it? I want to call it a hypothesis, but that's not right. A hypotenuse. Asymptote. Yeah, that's the word. Thank you. I couldn't remember. It has an asymptote at 0, but it's not bounded. It keeps going indefinitely this way. So you only need to define this edge of the function. Whereas when you have a box, like in the previous examples, or a triangle for that matter, you have two edges that you need to define. So you would make one of them t, and then you would make one of them whatever this distance is. So if this is like t, if this is 2, you do t minus 2 over here. Or if this is 4 across, you do t minus 4. Does that make sense?
Yeah. Does it matter which end you label as T?
I think you could probably do it either way, but it is, I always label the side the leading edge. So like we're sliding this function. Let's say this is our h of t function. This is our h of t. We're sliding this across some x of t function in that direction. So the side defined as t right now is our leading edge. I always try to define the leading edge as a t value.
Yeah, that personally makes more intuitive sense, because I just wanted to double check, because I know that Alpha and Mr. Will Knoll used t minus 1 as the leading edge of the signal as opposed to t. So yeah, okay.
The reason I used t minus 1 was because it was the question itself that specifies gonna be t minus 1.
Oh, okay.
It depends on your question though.
Yeah.
And you need to take careful look on it.
Okay. So we just should
Yep.
like be careful, basically.
Yeah. You just
don't
need to. Sorry.
Oh, just don't get tricked. Yeah.
Yeah. You just need to, again, my biggest piece of advice for convolution questions is just to practice, practice, practice. The more questions you do, the more intuitive it'll get and the more it'll make sense to you. That's really the biggest thing I can say. I really didn't understand convolution super well until like 4 days before our test. I sat down and I did like all of the convolution homework problems again and all of the convolution recitation problems again on my own. And that's when I really understood what was going on, was just doing that repetition. So, does anybody else have any other questions? Okay, I think we're going to call it there. Do give this problem a try, but don't beat yourself up over it because this is a difficult problem. It is probably, I don't know, 20 lines of integration to solve this. So give it a go, but don't spend hours doing it. Alrighty. Y'all have a good rest of your night.
Thank you, Will. Thank you, Amelia. Thank you, everyone, for coming.